So what are we going to do? I want to tell you a little bit about, first I'm going to spend a few sections, 3 sections here, telling you some things that are actually very standard, but maybe not known to all of you guys. And I apologize to those for whom it is something you all already know, either because you've heard it from me or you've heard it from someone else. And then I'm going to spend the second half talking about some things that I'm excited about that are, well, a little more new anyway. So what are we going to do? This is all going to be about Feynman integrals. And so the first thing we need is a graph. And so we're going to start by making the Feynman integrals in momentum space. So I'm going to take this graph, which you'll note is actually a multigraph, but good enough. And now what am I going to do? I'm going to assign momenta to the edges with momentum conservation at each vertex. And okay, that means I'm going to also have to choose some orientations here. Otherwise, it's not going to be well defined. And so I'm going to say, I'm going to take a Q1 and a Q2 and a Q3 and a Q4. And then I'll say there's a P1 and a P2 and a P3 and a P4. And now they're subject to momentum conservation. So I have Q1 plus Q2 is P1 plus P2. I also have that P1 plus P4 is equal to P3 plus Q3. I also have P2 plus P3 is equal to Q4 plus P4. And you want to think of these momenta as being vectors in R4. And the ones that are associated to these external half edges, or if you don't like half edges, you can put a vertex here at the ends. And so then to these edges incident to the leaves, they should be fixed. And then what do you want to do? Well, you want to integrate something, which I'll tell you what it is in a second, over all the free variables. And actually, I don't know how obvious it is to you guys, but in fact, it's really just a little bit of algebraic graph theory. Can anyone tell me what dimension the space is that we're integrating over? Well, and I'm not worried about the fact that there's already an R4. How many variables, how many R4 variables do I need to, am I actually integrating over free variables? Is that, do you see that from this setup or not? Well, I'll tell you in this example first, and as I'm telling you, you can continue to think about the general case, because I think it's actually kind of cute. So let's say that I keep the P1 and the P3, right? So I can certainly from this first equation solve for P2, and so I have Q1 plus Q2 minus P1, and from, say, this equation here, I could solve, I could solve for the P4. No, that's not the one I want to solve. Yeah, sure, I could solve for the P4. And so I say P4 is equal to P3 minus P1 plus Q3. And then the last equation doesn't really help me because it tells me something about the external momenta. It tells me that I have overall momentum conservation. All right, anyone have a nice thought about a nice way to phrase what the dimension here is that we're integrating over, or what the space is?
Well, we have a potential answer in the chat of 2.
Ooh, I should look at the chat. Sorry, that's right. I didn't make it visible to myself, and I will do that now.
And another answer as well.
Yeah, so what we're integrating over is the internal momenta. And so, yeah, sure enough, you might just say by some Euler's theorem that what you're integrating over is the cycle space, or the dimension. The dimension is the dimension of the cycle space. Okay, well, what is the integrand? Someone said, what are we integrating? And I deliberately didn't tell you until this page, because mostly I don't want to care too much about what we're integrating. So, well, what are we integrating? So let's, if we have our same graph again, All right, and what did we have? We had a Q1 coming in and a Q2 coming in and a Q3 and a Q4, and we had a P1 here, and we had a P2 here, and we had a P3, and we had a P4. And what do we want to integrate? We're just going to put a 1 over P squared for all of these guys. And now it's a 4 vector, so that really just means P dot P, norm P squared. That's the way the physicists write it. So I got a P1 squared, and I got a P3 squared. And then the other two, well, we have to remember what they were. What was P2? P2 was Q1 plus Q2 minus P1, norm squared. And then what was the P4? Well, the P4 was the, well, it was whatever we wrote it down on the other page to be. So I'm going to go and check because I'm already getting flustered by things going wrong. P3 minus P1 plus Q3. Okay, and so we're going to integrate that, D4 P1, D4 P3, and those are both integrals over R4. Okay, so that's fine. And for other field theories, if you're not, these are scalar integrals, and maybe you're not interested in scalar field theory because maybe you care about the real world and you'd really like to work with quantum electrodynamics, or you'd like to work with a standard model, or you'd like to work with whatever fancy thing the physicists tell you about. But the basic idea here remains the same. You're still in a situation where the edges contribute something, and they always write it to look like a factor, but in general, there can be tensor indices and you're using Einstein's summation convention. So in general, you're actually summing over a bunch of terms that are made of these factors. And then what are you integrating over? Well, you're integrating over all the momentum variables. So it's some sort of integral over r to the d valued flows, where d is the dimension of space-time. Which, as you'll notice for the example here, has been 4. So that's kind of nice. And I wanted to just note, in case you're ever listening to me or reading the physics papers on Feynman integration, is that the physicists call the cycles loops, and the loop number is the dimension of the cycle space. And you see that that was important here because it was what indexed what we're integrating over. Okay. I also want to point out, again, something that may be clear to many of you is that you can read off this integral from the signed incidence matrix of the graph. So, all right, we got our little graph again, and we're making things go this way. And now I'm going to ignore the external stuff for a moment, and we can talk about how we could put it in if we wanted to. For the moment. And if I now just make the signed incidence graph of that smaller piece, let's call the vertices 1, 2, and 3, 1, 2, and 3. And then we already called these edges P1, P2, P3, and P4 for their momenta. So let's just keep them in the same order. And actually, I don't know what convention you guys like for which sign goes with the tail and which sign goes with the head, but it doesn't really matter because the orientations were arbitrary anyway, as you guys can see. And so what are we going to do? We just have to put all these things in. And so I see a 1, -1, and a 1, -1. And then what's going on here, if you think about what the integral looks like, one of the ways you could write it, at least where I ignore the external stuff for the moment, is you could write it like this, oops, P2 squared, P3 squared, P4 squared. And then in the numerator, what are you putting? Well, you have to impose the momentum conservation. And so you need some delta functions to force some things to be the same. And you're going to get one of these delta functions for each vertex. So here's a vertex, and that's going to become this delta function. And what is that really? That's just the information that's in this row. And so the rows are the sets that preserve momentum. And so I don't even care if I did some row operations, or I'm looking at not actually looking at the signed incidence matrix, but some other representing matrix for the cyclomatroid of the graph. I'm totally happy, and I can read off the integral just as well. And if you did want to put the external momenta back in, well, you can make the matrix a bit bigger and you can just put those extra guys in, but you do have to mark them as different because those aren't variables that we now integrate over. So you do need to keep track of two different kinds of columns. Okay, so that's sort of what I wanted to say about that. And so that gives you, I hope that was slightly clear. I guess I should check what's in the chat. Okay, nothing new is in the chat. So that's how you write the momentum space integral of a scalar Feynman diagram. And you do something similar for a more general Feynman integral. Now, I'm going to tell you two other ways of writing down Feynman integrals. And I promise you that I don't actually care about integrals, but we will soon see two other ways to write it down. Are there any comments on the momentum space integral before I write down two other ways to write it? All right, here we go. As soon as one thing goes wrong, then suddenly everything goes wrong because everything's changed. This is not my computer, and so it's not quite the way I expected in all cases. Okay, let's do it another way. So I've got a graph. I'm always going to use the same graph today. And now so I should have said at the very beginning, what do you think of a Feynman diagram being? What are these graphs representing? They're representing little stories of particle interactions. You've got particles coming in and going out, and you have some stuff happening in the middle. And so you think this is sort of what you get out of a particle accelerator, because you've got particles coming in and you know what they are because they're the beams that you prepared. And you have particles coming out and you know what they are because you have detectors and they tell you what they are. And then there's stuff that happens in the middle of the collision and you don't really know what that stuff is. And ultimately, you're going to want to sum over all the possibilities. But one of the ways to index it is you say, okay, well, what are the ones that basically make the same graph? And then integrate over all the values for the edges that could do that. So values for the momenta of the edges that could do that. Or you could say, well, actually, I think I would rather integrate over all the values for the positions of the vertices. So let's call this x1, x2, x3. And now what do we want to do? Well, these xi's are still positions in space-time, and we're going to integrate them with each edge contributing 1 over x in minus x out. So again, I'm going to put some arbitrary orientations on here. And I am again ignoring, so I'm going to ignore external for the moment again. And then we're going to we would write an integral, and it would have, so we'd have an x1 minus an x2 squared, and we'd have an x1 minus an x3 squared, and we'd have an x2 minus an x3, well, and it's squared, so I don't really care, so I'll just there. But I guess I'm cheating. I shouldn't write it that way, should I? Because really one of the squares is a dot product and the other one is not. But it's the norm to the 4. d4x1, d4x2, d4x3. All right. And so there's something very nice to observe about this, that if I reinterpret, and what do I mean by that exactly? This is still, the denominator here is a product of squared stuff. Okay, the product of norm squares of some vectors. Well, what are those vectors? They're these little differences. Is there another way that I could think about these? And there is, because I can reinterpret this back in the original situation. So view the denominator as from a momentum space integral. And now what's happened? If I view this denominator as being given by some momentum space integral, well, I want to view the whole thing ultimately, but let's focus on the denominator for the moment. What am I seeing? I'm seeing a whole lot of edges whose momentum is the difference between one cycle variable and another cycle variable, one cycle variable and another cycle variable, one cycle variable and another cycle variable, and so on. Okay, and specifically, which cycle variables would these be? These would be ones that correspond to the vertices in the original graph, and what we have is a planar dual. So when you write down a position space Feynman integral in scalar field theory, then that is really just the momentum space Feynman integral of the dual graph and vice versa. And that's kind of nice because I don't know about you, but I like dual graphs. And it's particularly nice because now that's not how the physicists would think about it, right? They're not thinking of that as planar duality. They're thinking of it as coming from a Fourier transform. And the key to why this is a Fourier transform, so I'm going to just highlight the parts that are sort of the key parts here, because here we see essentially this is like 1 over p squared. And this part here is like 1 over x squared. And then what have we done in the middle? We've taken a Fourier transform. So that part's the Fourier transform part. And if we do that in 4 dimensions, we get something kind of special happening because it turns the 1 over p squared into a 1 over x squared. And so that lets us go from position space to momentum space. So specifically, how would I do this if I just sketch it out? So let's sketch it. The sketches of the derivation is going to look something like this. So we start with, in position space, we've got an integral over the vertices. And what is the integrand? The integrand is this difference of the 2 ends of the edge. And now if we just use the Fourier transform in there, then that artificially introduces now more integrals over the edges now. So I guess I should do this in the right order. So I get a new momentum variable p for each edge, which I'll call PE. And then I get to still have the d4v. And then I have, what integrand do I have? Well, I've still got, well, I've done this transformation. So I have the PE squared, and I've got the e to the minus I PE. And then this is the v in and the v out for the edge e. All right, so just as a rough sketch, that's what you get. But now what happens if you integrate it the other way? So let's keep the e integral out here. So what do I have here? I've got the d4PE. I've got the PE squared. So that's good. And then what do I have left? Well, I got a product over vertices. And now let's recollect this over the vertices. So collect every time a particular vertex shows up. Well, when is that going to happen? So e to the minus IV. Well, anytime there's an edge incident to v, you're going to get, well, either a plus PE or a minus PE, depending on what the orientation was. D4v. And now that's kind of nice because I'm sort of assuming you don't remember any Fourier integration and Fourier transforms. And certainly I didn't when I sit down to start thinking about these things. But we had 2 facts. One was the nice fact that said that 1 over p squared goes to 1 over x squared. And the second fact is that if you actually just Fourier transform nothing, Fourier transform 1, you get a Dirac delta function. And so that's exactly what's here. So this is going to be delta of that sum, but that's exactly the momentum conservation, i.e. momentum conservation at the vertices. So that's kind of nice. So the moral of this story is that Fourier transform is planar duality. And it's as simple as that when you're in 4 dimensions. All right, I have one more form of the integral I want to briefly tell you about. That's actually the one I'm most excited about. Does anyone have a comment or a question on that before I go on? So yet again, I'm afraid you have to suffer through one more integral transform. What is this one going to do? So let's start with the momentum space. So what was the momentum space? We're integrating over a basis of cycles. And what is the integrand? The integrand is just the PE squared, where PE is now the signed sum of the cycles that are going through that edge. And now I want to apply this. Okay, so what's going to happen? I'm going to have a whole bunch of 0 to infinity integrals. And what are they going to be? Well, there's one for each edge. And I'm going to call those variables a sub e. And then I get e to the minus ae pe squared. Okay, and I still better integrate over the other guys. Okay, and now you say, oh, well, too bad, I don't know how to do this integral. I don't know how to do this integral. But fortunately, it's not too hard because you can look it up on Wikipedia. If I do the C integrals first, this is actually just a Gaussian integral. So let's rewrite it. And again, you don't have to already know your Gaussian integrals. You don't have to already know your calculus because you can just look it up. So what does it look like? Let's write this. This is some quadratic form. And so let's write the matrix of the quadratic form. So there's some vector of the p's, and there's some matrix, and there's the vector of the p's. And then there's some more craft, which I'll tell you about in a second. And then there is what we're integrating over. All right, so the point is this is Gaussian. And so you can look it up. So look it up. But what's going to be important is to think about what's going to go in these two slots. So there's this slot and there's this slot. All right, I'm going to deal with this slot first because this is the slot we're actually going to ignore for today. So if I don't actually have something quadratic in one of the cycle variables, well, how could that happen? Because it is quadratic here in PE. So the only way I could fail to be actually quadratic in one of the cycle variables is if one of the external guys was playing a role here. So this is all stuff involving the external momenta. And so as we've been doing, we're going to ignore it. So set to 0 for now, for today, let's say. So I'm not going to say anything really more about the external stuff. The more interesting part is this part. So what is this matrix? Well, let's think about what the ijth entry is. Well, what could it have in it? All it can have in it is AE. So when does it contain AE? Well, it contains AE if PI, so the momentum for the ith cycle and the momentum for the jth cycle, both appear in E. So if both the ith and the jth cycle go through E. Okay, so now someone of you guys should be able to tell me what that matrix is. Let's see if someone told me in the chat what that matrix is. You know that. You know this matrix. You know exactly what this matrix is. I guarantee you know what this matrix is. Okay, fine. This is the problem with Zoom. It's hard to get people talking. And on top of it, I had a whole ton of technical problems. So as a result, everything is extra disorganized. And I apologize for that. Okay, so what is this matrix? Well, it's like the Laplacian, but I've taken a dual, right? I've got the cycles instead of the vertices, right? If this was about the edge has both I and J, has both vertices I and J incident, this would be exactly the Laplacian. But instead, it's a dual Laplacian. So dual Laplacian. And there's one other thing, is that there's these variables, right? So this is the dual Laplacian with edge variables instead of the dual Laplacian just with numbers for the edges. Okay, and now I already told you you could just go look up how to do the Gaussian integral, but this really is just a higher dimensional Gaussian integral. And so now you go look it up. And the answer is you get a determinant of that matrix. And normally you get a square root, a 1 over square root of the determinant. But remember, these are 4 integrals over 4 space. So you get 1 over square root to the power 4, i.e. you get 1 over the determinant squared. And so we're going to, for the rest, we're going to focus on the part without the external momenta. And now let's actually just define what we get here. We would get 1 over psi g squared, where psi g is the determinant of this dual Laplacian. And by the matrix tree theorem, you know what the determinant of a Laplacian is. And so if you think about it, you also know what the determinant of the dual Laplacian is. This is a sum over spanning trees. A product, normally you would take the edges in the tree, but you take the edges not in the tree, and that's the duality. And then it's the monomial of edges that you cut in order to make that polynomial, to make that tree, sorry. Okay, and this is have to be AE greater or equal to 0. And now I've noticed I have left out one part. So far we've said just dA1 down to dA, the number of edges of the graph. But now finally, somebody in the audience probably has been biting their tongue because I've written down a whole lot of integrals, but in fact, actually all been infinity. So that's not so good. Because this will be divergent, and renormalization is a different story that I wasn't going to talk about today. But we can fix it as long as the graph is in a certain sense critical. We can fix it just by setting one of the variables to 1. So I'm going to do that. So let's start integrating at 2 and just set A1 equals 1. And that's going to be this object PG, which you should think of as, so PG is what we call the period. And you should think of it as a residue, and a particularly important residue of the Feynman integral itself. And it's a particularly nice residue because it's, well, to say a little bit of the physics jargon, it's renormalization scheme independent. So there's a whole lot of choices that you normally would make to renormalize, and this number is independent of those choices. It's taken out all the external stuff, which we've been not worrying about so far anyway, and it gives you a nice and interesting number, theoretically interesting number. And so now I do know for sure that a number of you guys in this audience have heard me talk about this period before and talk about this dual Kirchhoff polynomial before, and some of the things that I like to do with the dual Kirchhoff polynomial and this period. I just want to emphasize the 2 Laplacian variants that we have here, because there are 2 interesting matrices here. And so one of them is what I already mentioned, this dual Laplacian. Right, and so it's here, and it's sort of indexed by cycles on each side by a basis of cycles, and other than that, it's behaving just like you would expect for a Laplacian. So you get a minus a if it's in those appropriate cycles, and you get a sum of them as you would expect. The other one I want to talk about is what I like to call the expanded Laplacian. And now, if you are very comfortable with your Schur complementation, you'll see that this is actually exactly the same thing, but well, it's the same. Well, the determinant, you'll see quickly that the determinant is the same thing by Schur complementation. But here I want to put the edge variables down this diagonal, so A1, A2, etc., down to A size of E. Make a little diagonal matrix here. Make a matrix of zeros here, and here I'm going to put E transpose, where E, that's a signed incidence matrix. But I want this to be full rank, so just remove a row. And I like this matrix. I'm going to call it M. I think it's a very nice matrix. It's fundamentally not that different from a Laplacian or a dual Laplacian. And if you think about how would you calculate a determinant of this, I said the word Schur complementation, and if you don't have that right at the tip of your fingers, what is it? It's basically block like block row reducing and then taking sort of a block cofactor expansion kind of thing. And so what do you get? You really do get exactly the E transpose and then the inverse of these guys. And so that will give you what you would expect from the normal. It'll give you exactly the dual Laplacian. Well, anyway, they're both nice matrices and they both have determinant, the Kirchhoff polynomial that we saw before. So let's see, I guess det M is psi G. And this guy, I didn't really give it a name. Do you guys have a favorite name for dual Laplacians? I don't know. I'm gonna call it L prime because I don't have anything else. I'm not actually gonna need a name for it. Okay. All right, that's the end of the overview of Feynman integrals in a way that I hope makes some connections that some of you would find interesting. Are there any questions about that part before I take 15 minutes, say, to tell you about some things that I think are exciting? Okay. Let's go on then. Oh, don't do that. Okay. The next thing I want to tell you is about cuts. But to tell you about cuts, I have to tell you about one more physics thing. And it is, what is the meaning of on shell? And again, I apologize. I don't know exactly what all of you guys know. And so if some of you guys are like, yeah, I know exactly what on shell is. Sorry, but I want to give you the picture for why it's called on shell. So first of all, we're going to work in a Minkowski space now. And I don't actually care what signature you use. We could say minus, plus, plus, plus. I don't really care. But the point is, your inner product is now not actually an inner product, because when you take the sum of the entry by entry products, you don't take them all with a plus sign. You should take, say, one of them with a minus sign and the rest with a plus sign. Or you could take one of them with a plus sign and the rest with a minus sign, or there's a couple other clever things you could do, but something like that. And so in particular, it's no longer true that if a vector squares to 0, that it is 0, because you have some negative signs and some plus signs. So there's lots of ways to get 0. And that's also true for it equaling a particular thing. And now, what is this sign difference representing physically? It's representing the fact that you have 3 dimensions of space and 1 dimension of time. And so if you want p squared equals 0, that gives you the light cone, right? Because you have some sort of, okay, there's my crummy old cone. What do you have? You have, well, the ordinary norm of the 3 space variables has to equal the norm of the time variable. And so you get a cone. That's exactly the equation of a cone. If you have some mass, then your p squared is not equal to 0, because if I have a massive particle, then this is like, I can't, if I have a massive particle, I can't be going at the speed of light. I am constrained. And instead of a nice light cone, you get some, some guy like this, where you have, you're living inside a light cone somewhere. And so this thing, this surface is called the mass shell, because that's, if you are behaving as a classical particle, you are constrained to living there. And so it's your mass shell. And a particle is on the mass shell or just on shell if it satisfies that. Now, when you're doing Feynman integrals, you have what are so-called virtual particles. The idea being that inside the Feynman diagram, where things are so sort of Planck small, then in fact you can go off the mass shell, but only inside, only in something you're going to integrate out, not in a final answer. Okay, so the point is, why did I tell you this? Is that putting an edge on shell is like cutting it. Because if you put it on shell, it's no longer a degree of freedom. It's no longer a thing you need to integrate. So That's what you want to remember, is on shell is cutting an edge. And furthermore, if you have a graph and you have some edge cut of the graph, so let's just draw an example graph. Here's a graph, it's got some stuff going on. Nice graph with one particle coming in and one going out. And now I could take an edge cut, I could take this edge cut, and I put it on shell. And there's non-zero external momentum on your side, so that's good. Otherwise, you get something trivial. Then calculating what's left, well, in this case, there's no integral because I've cut all the cycles, but there could be, if there was something left, there could still be a cycle to integrate over. That actually tells us something about the monodromy of the renormalized Feynman integral around the singularity that corresponds to, corresponds to the cut, basically. So the point is, there's a purely algebraic and in fact very combinatorial way of understanding these monodromies. You just need to understand how edge cuts behave. And it's not sufficient to cut into just two pieces. Sometimes you will need to cut into more pieces. And on the algebraic side, there are two co-interacting bialgebras here. So I mentioned in passing this Hopf algebra of renormalization, and I know many of you have heard me talk about the Hopf algebra of renormalization. And there's another bialgebra of the cuts. There's like a cut bialgebra, which essentially ends up being an incidence Hopf algebra of the edges. And those two bialgebras co-interact. And what that tells you, that gives you an algebraic avatar of how the monodromy around these singularities interacts with the renormalization. So if you're like me and you don't actually like integrals, despite having spent more than half an hour talking about them, this is exactly what you want to hear, because it tells you that really what's going on underneath is all algebra. Okay.
Sorry, can I ask a question?
Yep.
So by this cut, what you're doing, if I understand it, is that all of the edges which are cut by this red arc are going to be constrained by some mass shell condition. Is that right?
That's correct. Yes.
The same mass.
Well, I could potentially take this story where I have assigned masses to each of the edges. So it wouldn't have to be the same mass. You could have a different mass for each particle. It's simpler but you should view that mass as fixed. That's the point. The mass is no longer a variable you get to play with. It's some fixed value that, at least in principle, you could determine in an experiment.
But why do you lose the integration? I mean, you still have to integrate over this shell where this momentum still is constrained to. I don't see why do you lose somehow those integrations?
Well, it's
well, I can take it.
Yeah, no, yeah, you've lost almost all of it, basically. And then no, you're right. There's like one angle left, but you've lost enough of it that this is still the right way to think about it. Sorry, that's not a good answer.
And you want those to be positive masses. You don't want these to be on the cone themselves, on the light cone itself.
Yeah, I'm thinking, yes, I want to think about this in terms of positive masses.
Thank you.
Other questions? All right, I'm going to finish by telling you something that I've been excited about for many years. And as a result, I know some of you have heard about this before. So that Feynman period, remember the Feynman period was the one that morally is this guy, but of course I actually have to integrate over something and blah, blah, blah. It's controlled in some ways. If you put on your algebraic geometry hat for a moment, this guy is controlled by the geometry of the variety of vanishing of this polynomial. And there's another way that I can look at the geometry. I can look at it over a finite field. And so I'm going to define a piece of that. As long as your graph has at least 3 vertices, it turns out that if you take a point count, so let's see, I'm going to write it like this, and then I'm going to write in another color what that means. So that means the number of FP rational points on the variety psi g equals 0. So if you take that and your graph has at least 3 vertices, this will always be divisible by p squared. So let's do it, divide it by p squared, and take this modulo p. And now, why is this called C2? And what the heck is this all about? So the idea is you're turning this into something that's some sort of combination of counting and number theory, and so readily pretty computable. But it should still be telling you about the geometry. And in particular, back a number of decades ago now, I guess back in the 90s, so the periods that had been computed at that time were all expressible in terms of multiple zeta values. And Maxim Kontsevich said, well, if they're all multiple zeta, they should be that way for a good mathematical reason. And for a good mathematical reason meant that it's really because of the geometry, or you could say because of the motive. And if they were that way for that good mathematical reason, then this point count, this one here, would actually be a polynomial in P. And if it was a polynomial in P, then this is clearly the quadratic coefficient of the polynomial. And that's what the C is. The 2 of C2 is. It's coefficient 2. Okay, well, it turns out that's false. The conjecture is very false. You can get out of Minerva universality that you can, in fact, get arbitrarily bad geometries in here. But this still is a useful measure of how false it is for any particular graph. And so you see that things, well, these are some examples of how it does actually tell you something. So if the C2 is 0, then the period should have less than maximal transcendental weight. If the period is a multiple zeta, then this should be independent of P. And you can also get some slight extensions. So you can get the same sort of thing with a field extension, which ends up being the same as having something like a multiple zeta value, but with, say, 6 roots of unity and other things like that. And I'm not going to tell you what a multiple zeta value is, but it's a generalization of special values of the Riemann zeta function, and it's got some really nice number theory to it. And some of the C2 invariants have been proven to be coefficient sequences of modular forms. And in that case, the PG should be something more exotic. It should come from some evaluation of an L function of that form. And some of them are even worse. Some of them are unknown. So some are unknown. And they should be coming from something even more exotic for the period. Okay, but I want to be on my own computer. Okay, anyway. There's also some nice graph symmetries that are either proven or conjectured about the C2 invariant. So there's a completion invariance, and that's the one I'm going to tell you a little bit about in a second. So let me just briefly, I'm going to tell you about this, and I'm going to actually leave some of these other ones. There's some interesting cases. Duality is planar duality, so that one's fine. What is completion? Completion is if you have a 4 regular graph, let's let K be 4 regular, then completion says that it doesn't matter what vertex I remove. So C2 at K minus V should be C2 at K minus W. And it should not see which vertex you removed. And I bring this up to you because I think that's a really cool thing. And so far, some of the progress that was made, not what I'm going to tell you about today, but some other progress actually came about because I was chatting with the graph theorist, and he said, oh, I think I know something else that has that property. So it's a little bit weird, eh? I don't know if you guys know other things that have that kind of invariance. Okay, there are some other symmetries which I'll have to tell you about some other time. And I think because I'm pretty well out of time because my computer sort of failed, the point here is by using a few lemmas, a few algebraic lemmas, you can actually convert the problem of calculating C2 into a problem of calculating numbers of edge bipartitions. So the derivation is by the 2 lemmas on the previous page, but let me just tell you what the punchline is. So through some calculation using previous lemmas, in the end, what you get is that what is this? This is the parity of the number of edge bipartitions of, well, it's the graph G. This is in the situation where the graph G has a 3-valent vertex and the edges going into it are 1, 2, and 3. And so this is G, and let's call the blob inside H here. So the number of edge bipartitions of H with one part a spanning forest, and the other part a spanning tree, one part a spanning tree. Let's say the tree first, and then I'll tell you about the forest. and the other a spanning forest. But not just any one. It has to be a spanning forest where this vertex is in one of the trees and the other two vertices are in the other tree. So I'm just going to draw a picture to represent that. So I'm going to draw the graph, and then I'm going to say this color means that that vertex is in one of the trees, and these two being the same color means that those two vertices are in the same other tree. And there's only two trees. It's a two forest. Okay, so that's nice, because then once you have it reduced to a counting problem, then you can use counting to solve it. So you may have heard me talk like 3 years ago where I wrote down something very close to this, except there was one extra condition, that the graph K had to have an odd number of vertices. And my student Simone, just over the last year, has removed the odd number of vertices condition. And so now we can prove this whole thing for p equals 2, which is where I'm going to stop. So I apologize for all of the technical errors. Thank you for sticking around to listen. Yeah, thank you very much.
Thank you. Other questions for Karen?
Yeah, I could you just go back one slide, Karen? I was just wondering how, if you could tell us just a little bit about how you get there.
Yeah. As long as people don't mind sticking around to listen, that's the two previous slides. So the first part is that dividing by p squared is actually really annoying. And so at first you think, oh, who cares, divide by p squared? But you can actually get rid of it by processing 3 edges. And so if you use this notation for the minors of that expanded Laplacian, so then you take these 2 particular minors. And now I just need to reinterpret those 2 minors. And so then you just think about, what does it mean to remove, this is remove a row, this is remove rows, and this is remove columns. So that's how it's defining the minors. And so if you go back and look at the expanded Laplacian and think about what it means to remove rows and columns in this way, you will see that this ends up being the same as just the original, just the plain Kirchhoff, but for h. And this ends up being the polynomial that's the sum over those spanning forests of the type that I described before. And so, okay, so now you've reduced it to that, but how did it turn into counting something? This is where you need this other result, which is this corollary of Chevalley-Warning, which says that if you have a polynomial that has total degree n in n variables, then this point count is the same as taking a particular coefficient. And now this is particularly nice when p equals 2, because all these p minus 1s are just 1. And so when p equals 2, this says you're taking the coefficient that's just one copy of each edge variable in the polynomial. Well, if we go back here, what is the polynomial? The polynomial is one copy of this and one copy of that. And so, and I want to find one copy of each edge, so I just have to split them up between this and that. So I'm just counting edge by partitions, where on the one side you're a tree, and on the other side you're a forest, like this. And that's how it turns out. And then you just want the parity, because all these things are mod p, and we're working mod 2 here, so you just need the parity of it. Does that answer the question?
Yeah, thanks.
It's actually kind of fun. This proof here is there's a lot of like Math 239 in it, and you can go through the entire thing in about 2 hours, like really giving all the details. It's quite elementary, even though it's a conjecture. Well, the full conjecture, well, there's been basically no progress on the full conjecture, and some pretty serious algebraic geometers have thought about it. So it's one of these things that if you think about it in just a little bit more elementary way, it's actually easier.
I have a question.
Mm-hmm.
So if you usually view this as four regular graphs with one vertex removed or something.
Mhm.
So if they are planar, you can also think of them as medial graphs of something. So is there a relationship with the medial graphs?
I don't know. That's a good question.
Properties and this Kirchhoff polynomial?
Yeah, no, I don't know.
But you know
that's a
what
good
medial
question.
graph would be, right?
You know, I've
Mhm.
heard of medial graphs, but I don't remember. So if you could remind me, that would be nice.
Yeah, it's also, it's like you start with a graph, let's say planar graph, and then you put your vertex of, in the middle of each edge, you put a vertex, and that would be the degree 4 vertices. So then it's adjacent to the edges on the face, on the two faces containing that edge. And that
Yeah,
would be the
okay.
medial graph, yeah.
Okay, yeah, I have seen that guy. Yes.
Mhm.
But I don't know any I don't know any answer to your question though. But